Hello everyone, welcome to week 6 of the course. So in this week we will be starting discussion about pre-training models that we have discussed already. So we will talk about pre-training in the general sense, and then we will discuss what are different architectures with pre-training. So this is the topics we are covering in this lecture. What is pre-training? We will first talk about pre-training LSTMs, and that's where this IGNOU model will be discussed. And then we will talk about how do you pre-train transformers. So we will introduce the idea here, and we will discuss about various kind of pre-training architectures for transformers in this week. And that's what will give us large language models. What you're seeing on this slide are various popular LLMs, right? So you will have GPT-4 here, OPT model, NLB, Galactica, Chinchilla. And so they are all ranging from different number of parameters. Some are 11 billion, 530 billion, and so on. Some are even very small, like NLB is 54 billion parameters. It has very small versions also, and so on. Many of these are closed models and so on. So they are all mainly based on the transformer architecture, right? But it's not that transformer on its own becomes better than RNN. I mean, why these models are preferred is that they are including another very important idea apart from transformers. So we talked about GPT in the sense GPT, the T stands for transformers, but what is very crucial is P, and P stands for pre-training, and that is what is bringing out the idea of transfer learning. That you pre-train your model on a lot of data, and then you can use it for doing many other tasks with very small amount of data, right? Sometimes even without any data in context learning and so on. So transformers have become the go-to model for building large pre-trained language models, and which can be adapted for several tasks. And the idea of transfer learning, the idea of pre-training has been very, very central to this development. So to understand what is pre-training, let's first see how it's different from the standard supervised deep learning paradigm. So what is the supervised deep learning paradigm general? So let's say you have a task at hand, say spam detection. So your input will be a text, and you want to find out if it is spam or not, right? So how do you typically handle such task? So you first start by some data. So let's say you have some data where you have various different text, and somebody has labeled. So somebody has manually labeled them, this is spam, this is not spam. Now you would use this data to train a neural network, right, any model. So, and you start with some initialization, some random weights, and then based on this training you compute some loss, you update your parameters, and you will say, okay, I am training my model. So the parameters are trained from theta to theta star, and these theta star are what you use for a new task. Given a new email as input, you are detecting if it's not spam, right? So you need training the model so that you can update your parameters, and that will do the task for you, right? This is typically the paradigm. So you start from random initialization and you train your weights, right, for a task. But suppose from the same network you want to do another task, say sentiment classification. This may not work for you. You will have to again start from random and then take another data set, and you will say, okay, sentiment classification, right? So another theta star, you can call it for spam detection, and this is for sentiment. And you will need separate data set for doing both the tasks, and that's where you have a lot of data requirement for standard deep learning. Now think of it from application perspective. Now we are not just talking about general sentiment analysis and spam detection. We are talking about the field that has a lot of different domains. So you can think about domains like customer support, e-manuals domain. So think about you're having long e-manuals, and as a customer you have a question about this, that how can I encrypt my SD card? Now answer is lying somewhere in the manuals, but you need to really read the manual and answer that question. So you have a question answering problem where you want to question answer from these PDF files. Similarly, you can think about legal domain where you may have things like contracts, and from the model you want to find out in this contract what are the governing law and what is the covenant not to sue and perpetual and irrevocable license. You want to extract various clauses from this, right? So these are various clauses that you are extracting from this contract. So this is a problem specific to legal domain. Now you can talk about financial domain where, so let's say you have a financial, you are trying to write a financial report, and where one requirement is that for each numerical that you are putting, you need a tag for that. So there are standard XBRL tags. So you need to give an XBRL tag for this from this taxonomy. So this is a tagging problem that you have in the financial domain. So you need to know what this particular numerical actually means in the financial domain to be able to tag that. And then you may have biomedical domain and so on, where you have problem about named entity recognition, relation extraction, question answering. So you see, you have so many domains and you have so many different tasks across domains. You may have the same question answering problem in different flavors in different domains. No, so how would you use deep learning there, right? So you have the standard architectures, but that means you will start from random weights, and you will need a lot of data to be able to train such parameters. Like transformer model that we saw, simple encoder would have, if you go by the default transformer, 18 million parameters, right? So you need a lot of data to be able to train the parameters. So and it's very costly. Annotation is always very costly, right? How would you get sufficient, like 10,000 or millions of examples per task? You may not even have sufficient data for creating such annotation. You may not have trained manpower to annotate this. So and this becomes a huge issue, right? So that means you have this large language model, this large model where this, except from word vectors that you have learned, everything else is randomly initialized, and the training data that we have must be sufficient for learning everything about the task, right? So all the contextual aspect of the language you should be able to learn from the training data that you have at your disposal. So that's where the particular this paradigm came that made a very huge impact on this field, and that is what is pre-training. Okay, so and this is also known as pre-trained fine-tuning paradigm that we will discuss, I mean, this lecture and the next. So, and this typically started from 2018 in the field of NLP, and this has been there in the other fields also, like computer vision and so on. So what is the idea? So we are again having the same setup. So we have a neural network and we have random weights, right? But rather than starting from the task, like rather than training it for a task, what we are doing different is that we are saying we are dividing this into two stages. In the first stage, we will simply pre-train a model, and for pre-training we will use everything at our disposal, and we would need something where we will need data where we do not need human labels, and that's where the idea of self-supervised learning comes in. So I need to use data where no human label is required, right? So something like I need all the web data and I will just predict what is the next word, simple language modeling task, right? Or I can remove some word and predict it. So we will discuss about this. Right? So here you don't need any human labels. You can just take the data on the web and you can create the synthetic train input output pair for your model, right? And the model learns how to predict next word. Right? And once you have done it, you already have some theta star pre-trained weights, and then you are ready. You are saying, okay, I have already got a very good initialization pre-trained weights. Now whatever task you want me to do, I have sufficient knowledge, but I will still just fine tune it around this. So I'll say, okay, give me some hundreds example or 1,000 example, and I can now use this to do spam detection from the pre-trained model. I can do sentiment classification from this pre-trained model, and so on, right? So I will start from pre-trained weights, and then now you give me again text and labels like you were doing earlier. in only a single stage, but now you are doing in the second stage. And but I'll start from these weights, right? I'll not start from the random weights, and I'll just fine tune around that, right, to get a sweet spot for my model. So that's the difference that we get, right? And the way we do this first stage, right? So this is the key idea of transfer learning. So we have learned a lot from some task, and we transfer it to new tasks, right? So we have learned a lot from language modeling task, and we transfer that knowledge to other tasks. So the typical choice is the language modeling task, right? So idea is that you take a vast neural network, so it can be transformer or LSTM architecture, and you train it on huge data, right? And then whatever you've learned, you transfer it to any target task in NLP that we care about, right? You use it for NER on biomedical domain, you use it for something in financial domain, right? And this has been a very successful idea in NLP, right? So earlier people used to require millions of examples in supervised models because of huge architectures, but if you use language models as a starting point, you can just use thousands or even a small number of examples for doing the same task, even with better accuracy, right? So what does a model actually learn from pre-training? So you may say, okay, you are just predicting the next word, but do you really learn something meaningful? Now you see, we are talking about everything on the web, right? All the data that we have on the web. So you would have all kind of data. So let's say there are canines everywhere, one dog in the front room and 2 dogs, right? So you're learning the plural of dog is dogs, right? By predicting the next word. So it wasn't just big, it was enormous, right? So you're predicting this, right? So it is from big you can get enormous, right? So the author of A Room of One's Own is Virginia Woolf. So you're learning, predicting the name of an author. So you're learning the next word of this author. The doctor told me that you're learning how to predict the pronoun, right, of a word. The square root of 4 is, right, so predict 2, you're actually learning some math skill, that the square root of 4 is 2, right. So you see, you are learning different type of tasks while you are actually doing just the next word prediction, because the web is full of data set of different genres, right. So that's the idea. So you are taking all the text available on the web, but it contains enormous amounts of knowledge, right. And if you pre-train on this lot of data with all the knowledge that you have, so this is what language will give language model the ability to do so much that we are seeing, right. So you can pre-train on this huge data, and then it gets ability to do so many different types of things. Now, what kind of data people use? So typically, Common Crawl is the data set that has entire web snapshot produced by non-profit Common Crawl with billions of pages. So we also use a very popular data set is C4, that is Colossal Clean Crawl Corpus, so which has 156 billion tokens of English which are filtered. It has mostly patent text documents, Wikipedia and news sites. So another very popular pre-training corpus is called the Pile, so which has data from academics, web, books, lot of dialogue data set. So academics, you have all the archive data set and PubMed Central and so on. So web, you have whole stack exchange, right? So you can answer all the questions that are asked are there. Whole Wikipedia is available, even GitHub is available, right? So there's a different types of data set, different books are available. So you take all this data set and just do the task of learning next word, right? And in doing that, you are learning so many different aspects about human knowledge, and that's what would help you in the new task that you want to do. Of course, while you take the data, there are various aspects that one has to take into account, like how to maintain the quality and safety, and which are a little bit subjective, right? So many LLMs, they attempt to match Wikipedia, books, popular websites, and they need to remove adult content and so on. And there are various deduplication that they have to do at various stages, right? So this is what they have to maintain the quality, and in safety they have to ensure that you are not including toxic content, because whatever you are giving it to learn is what it is learning, right? So it doesn't have an internal filter on what which data I should learn and which I should not learn, right? So whatever data you are giving, it is learning. So it's important that while you are pre-training, you remove all the noises, right, and all the unsafe things that are on the web. So of course, there are issues like how do you automatically detect this at a scale, because sometimes what people have seen, so if you use certain filters, it even removes dialects, various dialects that are not very common, it removes that. So yeah, this is a subjective thing and typically very important while creating your data set. So now coming back to our pre-training fine-tuning paradigm. So what we said, so we can pre-train using language modeling. So we can take any architecture like transformer or LSTM, and we give it a lot of data on the web and let it just predict the next word. So arrow goes to make tasty tea, and you predict the next word, right? Goes predict to. So you do predict next word, right? And keep on doing that. And once you have done this, so you already have a good initialization. And then once you have that good initialization, you now fine tune it for various tasks. So you have a pre-trained model, and now you say, okay, now give me some labels, not many labels, and I will be able to adapt to that task. So give me sentiment analysis, some data, input and output pairs, and I will adapt it. Now we will learn how exactly we adapt this, how exactly this fine tuning works, but that's the central idea, right? Rather than going from theta to complete sentiment analysis, random weights complete sentiment analysis, we say no, we will go random to theta pre-train, and then I will do sentiment analysis, and there the data requirement is less. Where this path data requirement was huge. And now I can do various tasks. So I can say, okay, now from here I can do classification, I can do NER. I will use different parameters, but I will start from pre-train only, and I need little data, right, to pre-train to further fine tune my model. So it's not that people just got pre-training over transformers. Even before transformers, there were LSTMs, and people tried pre-training on LSTM, and that's why the IGNOU model was very popular before pre-trained transformers came in. So idea is that we learned in LSTM you can have forward and backward LSTM. So what if you train both direction LSTMs? So I'm training a forward LSTM and a backward LSTM, right? So open a bank, I'm predicting the next words, and here you are going from back, predicting the previous words, bank A, open, start of sentence. Now what you will do, so suppose you train this forward and backward LSTM over a lot of data. Now given a new example, like what you can apply this example over this pre-trained LSTM, both forward and backward direction, and you can get this contextual, you can get this hidden vectors, and these hidden vectors are your knowledge, pre-trained knowledge, right? So because you have trained your model on the entire data set, you are getting these hidden vectors that have knowledge over the entire data set, right? So you use these hidden vectors in your new task, right? You directly use the hidden vectors and then perform your task. So that is the idea, and you can combine both forward and backward direction hidden vectors. So that's the secret. So suppose so they actually trained multi-layer LSTM. So 2 layers is what they had used. So you apply the word embeddings, then you have 2 H1 layer 1, I mean H1, H2, H3, H3 at layer 2, and at the final layer you apply this feed forward and softmax, and you predict the next word, right? That's how you train a language model over LSTM. You also train a backward language model in the same way. So you go backwards to sticklets, and you train what is the previous word, train to predict what is the previous word, and this is again in multi-layer, right? So you have trained both forward and backward, right? You can train them independently, they don't need to interact while training. But now once you have trained them, you want to combine the power of both the language models, forward and backward language models, to do a specific task, right? So what is done? So suppose now they are trained. So on a given task, you want to make use of this knowledge. So what you will do, you will say, okay, so let's say I have a word stick. I will actually have whole sentence. Let's say in the sentence I have the word stick. So I will pass the sentence through both forward and backward LSTM that are pre-trained, and I'll get this embedding layer 1 and layer 2 hidden vectors, right. And now I'll concatenate these hidden layers from forward and backward at all the 3 layers starting from embedding, and then I can say, okay, why don't I make use of all the 3 embedding layers? So I can give them some weights. So because they will have the same dimension, so I can ensure that they have the same dimension. I can give some weights. So let's say S0 is the weight given to embedding, word embedding, S1 to the first hidden layer, S2 to the second hidden layer. So I can use a weighted average of the 3 layers, and this becomes my embedding of the word, right. And this is what is capturing the entire knowledge that I have learned. So it does not have a simple word embedding. This is a contextual embedding that is learned over the entire data. So this was the paper published in NAACL 2018. So deep contextualized word representation, and it learned task specific combination of bidirectional LM representation. And there was of course a previous model tag LM by the same authors, where they just use the top layer of LSTM, but they said, okay, why don't we use all the layers? So you have a L layer bidirectional language model, and let's say you have the embedding and the hidden states, both forward and backward direction. So K denotes the token Tk and J denotes the layer J, right. So for each token K, you will have Xk, the embedding, you have Hk at layer J forward, Hk at layer J backward, right. So that's what you have, and you can also now say this is like Hk0, this embedding, right. So you have this Hk_JLM, right. So now, and you have it at layer 0 up to layer L. Now you can combine these representation that you are learning at multiple layers into a single embedding. So you have the task specific representation for each token. So this is what we saw. Now you can say, okay, I'll use some weighted average of all these hidden states and embedding for all the layers, and the entire thing can be multiplied by task specific parameter, that is how useful the embedding will be for the task. So S task are task specific mixture model weights, and gamma task is the importance of Elmo to the task, right. So you may have these 2 hyperparameters that you can tune per task, right. So and then what you will do with this, right, I mean, so let's say you are doing an NER task. So you are predicting location, like beginning of location, end of location, and so on. So you will have some input, New York is located. Like you are doing with RNNs, you will first get the embeddings. So embeddings can be obtained, say, character level models or token embeddings directly, or you can combine all of these. You can even apply pause embedding. So there are so many things you can do, but you will get an embedding, right. So you will get a final embedding. So once you have the embedding, these are the inputs to the RNN, and then you apply your normal bidirectional RNN or whatever, and you get the hidden states. So these are your hidden states, right. Now where exactly you are using Elmo? So that's why you say, okay, now this same sentence I can pass through this pre-trained model. So this is a pre-trained model where I know all the parameters. See here, I don't know the parameters for this RNN, right. So I am training these parameters, but these parameters I already know. So I can say I can pass it through this, and because I know all the parameters, I will get these representations, the hidden layers and whatever, right, all the layers. I will get the representation because the parameters are fixed, and I have seen how to combine these into a single embedding for each word. So suppose for the word new, I combine all of these into something, and I'll say, okay, both forward and backward direction, I'll have the final output, and I concatenate it with the hidden vector, right. So this was something I was learning from my current by RNN, but this is something I have transferred from a pre-trained model, right. And then I can concatenate these two and use that to learn the further representations, and then I go to dense layer and train my loss, right. And this loss will only update the parameters of my by RNN. This will not change now. This is already frozen. I am just transferring the knowledge here, right. So you learn this, and this the way you combine this into this, you can do a task weighted average of multiple hidden layers. Right. So what they did in the experiment, they used the 2 by LSTM layers. So they have different usage. For example, they found the lower layer was better for lower level tasks, like if you are doing part of speech tagging, syntax dependency, NER, you should have given the more weightage to the lower layer. But if you are doing more semantic level tasks like sentiment analysis or semantic role labeling, question answering, SNLI, etc., then you have to give more weight to the higher order layer. Right. So you can give different task specific weight to different layers while you are combining. Right. And they found some huge improvements with layers. I mean, this was one of the first papers that showed that from the same model you can show improvements across tasks. Otherwise, previously people used to have papers on one task, right, separate papers for each task. So what they saw, this is the previous SOTA, and previous SOTA for all the tasks were different models, right. So on NLI and NER and co-reference, there were different models that were the state-of-the-art models. And if you just use the RNN with the data without this pre-training idea, you would still get below state-of-the-art, right. So the numbers were not matching because this would use much more tricks. So then they used their idea that okay, I can't beat it with the simple RNN, but what if I pre-train this ALMO model on huge data, and then I transfer that weights to this model, and you see a huge boost, right. So you get huge improvements, and this of course does better than the normal RNN, but it even beats the previous state-of-the-art in all the cases, and that was like a good revelation that people had at that point of time. Okay, and even they saw that okay, so it becomes more efficient to fine tune with ALMO. So what you are seeing on x-axis is the amount of data that you are giving, and y-axis is the performance, right. So if you just give 0.1% of the data, so this is baseline model, it doesn't do well, like in SNLI 50% is just like close to random, but here this model even with 0.1% data giving much better than the baseline, right. Same here for SRL task, and like even with 1% data it is giving quite good performance. So when you have a small amount of data, it's much better to use a pre-trained model because this will give you much better accuracy than a baseline model. Even with 100% data you get improvement, but the improvements are much higher when you have a small amount of data. So when you have a small amount of data, then you get huge improvements compared to the baseline with the current, with the pre-trained model. So this was such an important finding. Now you can do this simple problem, to get an idea of how do you weight multiple layers. So let's say you have a 2-layer forward and 2-layer backward model for LM for ALMO, and given a word, you have its embedding 0.2, 0.4, minus 0.5. This is the word embedding, and for the first and second layer for the forward LM, you have separate weights. So 0.2, 0.4, 0.7, 0.3, 0.6, 0.5. This is layer 1. This is layer 2 for forward LM. Similarly, for backward LM, you have 0.2, minus 0.4, 0.7, 0.3, 0.6, minus 0.5, right? And assume that because you have to get a single representation, so you will have softmax normalized mixture weight. So these are given by 0.2, 0.3, 0.5. So how do you get a final representation? You do 0.2 times this, 0.3 times this, 0.5 times this, and this will be you get a 6-dimensional, 3-dimension here, 3-dimension here, forward, backward, 6-dimension representation, right? So you can find out what will be that 6-dimension representation for ALMO by taking a mixture model weights for these embeddings. Now, what can you say about the task, right? So how do you know what kind of task is being done? So this will depend on how much weight you have put for various layers. So if you are putting higher weight on the higher layer, that means it's more semantic level tasks like sentiment analysis or semantic role labeling, that kind of task that you are doing. Okay. So next we will talk about how do we use transformers for pre-training, right? So we have discussed transformers in huge detail. Now a transformer, you talk about encoder, you can talk about decoder. So when I'm saying pre-training, what exactly I am pre-training? So there are three kind of architectures we can use, right? Because we have encoder and decoder. I can just pre-train decoder, and that is actually one of the default methods for doing pre-training. So you just pre-train the decoder, and that is what has given the models like GPT, Claude, Llama, mixed-train models. I can pre-train just the encoders, and that is what has given the BERT family. So I just pre-train the encoder models, right? Or I can pre-train both encoder decoder together, and that has given BART model. There was T5 model, and then there's an instruction fine-tuned version of T5 called FLAN T5 model, and these are all very popular architectures. Now in this week itself, we will see how to do pre-training with different architectures. We will not talk about FLAN T5 directly, that we will do in one of the later weeks, so when we will talk about instruction fine-tuning, but others we will discuss in this week's lecture itself. So we'll see how to pre-train them and how to also use them for various fine-tuning tasks. Okay. So you can read more about this in chapter 10 of our SLB book. Okay then, thank you.